Hi everyone, once again welcome to your channel TKG Physics Classes and welcome to your new lecture from friction. All of you know our ongoing chapter, that is laws of motion, and are on the ongoing topic that is named as friction. We already completed 2 lectures related to friction. Now this is our lecture number 3, and in this lecture we will discuss, that is today our key point, work done against friction. We will calculate, we will derive the expression of work done against friction when the body is placed on a rough horizontal surface, when the body is moving up in an inclined plane, when the body is moving down in an inclined plane, etc. Okay, so before going to that part, at first you just recall the previous classes, what you learned from the last 2 lectures related to friction. So from last 2 lectures we discussed that the friction, types of friction, static friction, limiting friction, kinetic friction, when we apply static, when we apply kinetic. Then we discussed the laws of friction, we discussed angle of friction, angle of repose, the relation between angle of friction and angle of repose. So those who are new in this channel and watching this video, I strongly recommend it, just go back to the previous classes, learn the basic concept, then come to this topic. Okay, so in this lecture we will discuss work done against friction, and first case, that is we will discuss the work done in sliding a body over a horizontal surface. Okay, let's check it. So our condition, that is a body is placed on a horizontal surface. You see, this is a body of mass m is placed on a horizontal surface. So obviously here weight W, that is equal to mg, is directed vertically downward, and this weight is balanced with the upward normal reaction force. This weight is balanced with this normal reaction force. So this is R, and the body is moving. So obviously when the body is moving, that means in the forward direction there is an applied force. So capital F is the force which is applied horizontally, and for this capital F the body is moving in the horizontal surface. Okay, so this is the you see written this part. Consider a body of weight mg resting on a rough horizontal surface. Suppose capital F is applied horizontally, and so that the body just begins to slide. So this is the condition, this is the applied force when the body just begins to slide. That is the initial condition for its motion. Okay, so after some time the body covers some distance. So this is the distance. Now this is the new position of that body. So here you can also write this one, weight, that is mg downward. There is the normal reaction force R, there is a forward force F. Now see, when external force F is along directed positive x-axis, in the opposite direction, that side, in the opposite direction, there is a frictional force. Now question is, this frictional force is static or kinetic? You see, this is the applied force when the body just begins to move. This is the limiting condition, and after that just begins to move. So this is the kinetic friction, Fk. Now you have to calculate work done. So these are our forces, various forces which is shown in this figure. 4 forces basically: weight mg downward, which is balanced with normal reaction force upward, external force F, that is forward direction, and in the backward direction there is a kinetic frictional force, that is Fk. Okay, so all of you I think know the expression of work done. The work done against friction, work done against friction, you know the basic formula of work done, W, that is equal to F vector dot S vector. We will discuss this part in next chapter, which is named as work energy power. Work done is a dot product of force and displacement, and you know the dot product meaning, that is Fs cos theta. We already completed vector chapter, the scalar product or dot product of 2 vectors. So the dot product of 2 vectors Fs, that means Fs cos theta. Now here you see force is applied along the horizontal direction and the body is displaced along the same direction. That is, the direction of S and the direction of F are same. So here theta is equal to 0 degree. So W, that is equal to Fs cos 0, because F and S are along the same direction. So this result will be F into S. So the expression of work done, that is F into S. Now question is, this is the F, that is the applied force which is just applied on the body, for the body just begins to slide, and that condition, that means this force is balanced with this one. Suppose 10 Newton force is required for moving this body, for just begins to move. So just begins to move, that means there is a backward force that is also 10. So this is the initial condition. Now when you apply 11 Newton force, when you apply 12 Newton force, the body is moving forward, the body is under motion. But the beginning, the basic, there is a minimum force required for the just movement of the body, that is equal to 10 Newton, and which is exactly equal to Fk. So here in the place of F, you can write Fk into S. Now what is Fk? Fk, that is equal to mu k into R into S. We already completed this one. Now R is balanced with mg, weight. So this value will be W, that is equal to mu k mg into S. This is the expression of work done, students. This is the expression of work done in sliding a body over a horizontal surface. This is our first theory, first derivation. Okay, you can take a screenshot. Now we will discuss the second part. Okay, so our second topic, that is, okay, just remove this one. Okay, up to this portion. Our second topic, work done in not sliding, in moving, right here, work done in moving a body up into an inclined plane. Moving a body up in the inclined plane. This is the second condition. So draw the diagram. This is the horizontal surface. This is an inclined plane. Here body of mass m is situated here. So this angle is known as angle of inclination, suppose theta. Okay, now weight W, that is mg, is directed vertically downward. This angle is theta, that means this angle must be theta. So this component will be mg cos theta, and this component will be mg sin theta. Now suppose an external force capital F is applied along this direction, so that the body just begins to move. The body just begins to move up in the inclined plane. So this is the initial, the basic external force. Now in the upward direction there will be a normal reaction force. Now see, external force applied along this direction, so obviously there is a frictional force which is directed opposite to the external force. So F is directed along this direction, so frictional force will be along this direction. So here there is a frictional force which is named as Fk, which is directed opposite to the applied force. Now you check this one. So same thing, write it first. Consider a body of weight mg, mass m, so weight mg, not resting. Suppose here you write placed on a inclined plane. Placed on a inclined plane. And after that you write, suppose a force capital F is applied, so that the body just begins to move up, moves up in the inclined plane, okay, this is the basic. Now you write, let Fk is the coefficient, the force of kinetic friction. Fk is the kinetic friction which is directed opposite to the direction of capital F. Now you see here mg cos theta is balanced with R. that means here you at first you write mg is direct component form divided. Here mg has two components. Point 1, mg cos theta, which is balanced with which one? Mg cos theta, which is balanced with normal reaction, which is named as normal reaction force, that is capital R, and another component that is mg sin theta, which is directed in which direction? You see, downward to the inclined plane. This is the upward to the inclined plane, and this is the downward to the inclined plane. Now we have to find out the force. Here you see external force capital F in the upward direction, and in the downward to the inclined plane there are two forces. One that is mg sin theta, another one that is Fk. So the downward to the inclined plane, the net force, the total force, that is mg sin theta plus Fk, and upward force, that is capital F. So what is the initial condition when the body just begins to move up? See, you just imagine what is the initial condition. If this force is 10 Newton, suppose, so the addition of these two forces, that is mg sin theta plus Fk, must be 10 Newton. Downward direction 10, upward direction 10. So this is the basic concept when the body just moves to up. Now when the force in the upward direction will be 11 Newton and the body will be moving upward, so the minimum force which is required for moving the body upward, that is the capital F, is equal to the addition of downward forces, that is mg sin theta plus Fk. Write it. So here the minimum force which is required, write it, the minimum force which is required, the body moves up in the inclined plane, that is capital F, is equal to mg sin theta plus of Fk. Now you can easily find out the value of Fk. You already know this one, that is Fk. Okay, you write here, that is F is equal to mg sin theta plus Fk, that means mu k into R. In next part, that is F equal to mg sin theta plus mu k is remains same, and what is R here? R is balanced with mg cos theta, that is mg cos theta. Okay, so this is the expression of force. Here. Suppose this is our equation number 1. But you have to calculate the work done. So same thing, work done, write it. The work done, W, that is equal to F dot S, and F dot S, that is F is cos theta and theta is 0 degree. Why 0 degree? You are applying force along this direction and the body is moving upward, so the direction of S and the direction of force, that is the same. So theta 0 and theta 0, that means this value will be only F into S. And you know the value of F. This one is the value of F, right? That is, you take common mg, here mg and there is mg, so force F, that is equal to mg, there is sin theta plus of, and there is mu k cos theta. This is the value of F and multiply it with S. So this is the expression of work done, students. This is the expression of work done when the body is moving, moves upward, just moves upward to the inclined plane. Okay, see, that is W equal to mg. M is the mass of the body, G is the acceleration due to gravity, theta is the angle of inclination. This is the theta, horizontal to inclined plane, the angle of inclination. Mu is the coefficient of kinetic friction. S is the distance traveled by the body. Okay, so this is our second derivation. Now third part, that is we will derive the expression of work done in moving a body not up down to the inclined plane. Okay, right. Our third point, so you remove this one, you write here work done in moving a body. This one is down, not up, in the inclined plane. At first draw the diagram. This is the horizontal surface, this is the inclined plane, this is the body of mass m, weight, this angle theta, angle of inclination, weight w, that is mg. So this component has mg cos theta, which is balanced with normal direction r. This is mg cos theta, which is balanced with normal direction r. This component is mg sin theta, and here external force applied along that direction. External force is applied in the downward direction. So obviously in that direction there is a frictional force Fk. Now again here you see this W, that is mg, weight of the body, has two components. So at first you write this thing, a consider a body of weight mg placed on an inclined plane, same. Now suppose an external force F is applied so that the body just begins to move not up, this one will be down, begins to move down in the inclined plane, and this is the force where the body just begins to move in the down to the inclined plane. This is the initial and the basic applied force, initial. And here Fk is the frictional force. So right here mg has two components. First one, that is mg cos theta, which is balanced with which one? Mg cos theta balanced with r. And second one, mg sin theta, which is directed in which direction? See, down to the inclined plane, downward to the, which is directed downward to the inclined plane. Now again you see, check, Fk is the force which is directed upward, and capital F and mg sin theta, two forces which is directed downward to the inclined plane. So what is the value of capital F here? Right, upward force, that is equal to sum of the downward forces. So sum of the downward forces, that is F plus mg sin theta, that is equal to upward, that is Fk. So here F, that is must be Fk minus mg sin theta. This is the net force. Okay, now you use, that is F is equal to, in the place of Fk you can write mu k into r, that is mu k into r minus mg sin theta. Now you know the value of r. Here mu k and r is balanced with mg cos theta, that is mg cos theta minus of mg sin theta. Okay, now you can take common, that is F equal to mg common, so this one is mu k cos theta minus of sin theta. But student, is very important point, one important point here, this angle of inclination theta is related to coefficient of angle of repose, in which relation this theta is less than angle of repose, greater than, or equal to. You just imagine angle of repose, that means the angle, the minimum angle for which the body just begins to slide down. Okay, so for angle of repose the body just begins to slide down, that means there is no need to apply an external force for moving the body in the downward direction. So here this angle, the angle of inclination theta, must be less than the angle of repose. This is important, student. So right here theta is less than angle of repose, but because for angle of repose, the body, if theta is equal to angle of repose, the body is automatically moves down to the inclined plane. This is the definition of angle of repose. So theta must be less than the angle of repose. Okay. So this is our expression of force. So what will be the work done, right? So work done, that is equal to F into S, and in the place of F you can write this value, this one. So this one is mg mu k cos theta minus sin theta multiple of S. So this is the final expression. This is the final expression of work done when a body is moving downward, moving down in the inclined plane, just begins to down. This is the basic initial condition. Now if the surface is not rough, in the place of mu k, here you have to write 0. If the surface is smooth, there is no coefficient of friction, in the place of mu k you have to write 0. Then the expression of W will be, you just simplify. Okay, but in general a surface have a coefficient of frictional force. So this is a general formula. Okay, this is our theory number 3. Now last part, we will derive an expression of acceleration. Okay, write it. So our fourth one, that is acceleration of a body sliding down. Acceleration of a body, here you write acceleration of a body sliding down to the inclined plane, sliding down to the inclined plane. Okay, so consider a body of mass m, that is weight mg, is placed on an inclined plane first, but here no external force is applied. This point is not needed here. No external force is applied on that body. Now you just divide this component. Mg is directed vertically downward, so this component is mg cos theta, this component is mg sin theta. Okay, so when mg sin theta is the downward direction, Fk will be in the upward direction. This is the value of Fk, just opposite to the, because the force mg cos theta, this is the only force which is directed downward, that is mg cos theta, is with the help of mg cos theta the body is moving slide down. So when the body is moving slide down this direction, in the opposite direction there is a frictional force Fk. So what is the net force here for which the body is moving, is going slide down? What is the net force? Suppose mg sin theta is 10 and Fk is 6. So what is the net force here? 10 minus 6. The net amount of force which is help the body to moving downward direction, that is mg sin theta minus Fk. There is no external force. So what is the condition? Theta is related with angle of repose here, angle of repose. You see, when theta is less than angle of repose, that means here you have to apply an external force for the moving body in the downward direction. But when theta is equal to angle of repose, that means the body just begins to moving downward. So for just begins to moving downward, theta must be equal to angle of repose. So here the body is moving in the downward direction, so we consider the angle of repose, theta, that is the angle of inclination, is more than the angle of repose. Okay, so this is greater than. Now you write here Fk is the coefficient of friction, and mg has same thing. Mg has two component, one mg cos theta which is balanced with normal direction r, and mg sin theta which is directed downward to the inclined plane. So the net force for which the body moving downward that is mg sin theta minus of Fk. This is the net force, because mg sin theta helping the body moving downward and Fk is opposing the body for moving downward. So Fa, that is mass into acceleration, is mg sin theta, and Fk, that is mu k into r. Now in the place of r you can write r is balanced with mg cos theta. So you see m cancel out, so acceleration A, that is equal to g sin theta minus of mu k g cos theta. You can take a common g, so when g will be common, this one will be A equal to g sin theta minus mu k cos theta. This is the expression of acceleration for which the body is moving downward. This is the value of acceleration. Okay, and you have to remember one important point here: there is no external force applied. The body is moving, and when no external force applied, the body is moving downward with the help of this component. That means theta must be greater than angle of repose. Okay, so students, this is the theoretical part. Now we'll solve 2 or 3 numericals related to this problem. Okay, solve it. So we will solve some numericals. Okay, let's take problem 1. In problem 1, given a mass of 200 kg is resting on a rough inclined plane. According to our problem, at first you draw the diagram. Okay, draw it. So problem 1, mass m, that is given 200 kg, mu given, that is 1 upon root 3, and resting on an inclined plane at an angle of 30 degrees. So angle of inclination theta is given 30 degree. Now you have to find out the least and the greatest force acting parallel to the plane to keep the mass in equilibrium. Okay, suppose this is an inclined plane, mass m is situated here, so mg downward, this angle theta, so this angle theta, this is mg cos theta, this component mg sin theta, and here frictional force F, and here applied force, suppose F1. This is our first condition. And our second figure, like this way: suppose a body of mass m is placed here, mg downward, this angle is theta, so this component is mg cos theta, this component mg sin theta, here applied force F2 along upward, and frictional force in the downward. Okay, now you see, you have to find out the least and the greatest force, minimum and the maximum force, which is required and which is directed parallel to the plane of the body, and the body must be in equilibrium. Okay, you see, if we apply this one, at first you find out the value of r. Okay, you find out the value of mu, that is equal to, F, that is equal to mu into r, not Fs, not Fk, because here in question that is coefficient of friction mu given, not given mu s and mu k. So F equal to mu into r, and mu and r, that is balanced with mg cos theta for both cases. So mu, that is 1 upon root 3, mass 200, g 9.8, and cos 30, and cos 30 value, that is root 3 by 2. So this root 3 cancel out, this one is 100, so 100 into 9.8, so that is 980 Newton. Okay, this is the value of F. Now you find the value of mg sin phi. At first find this, that is mg sin, not phi, theta, that is m 200, g 9.8, and sin 30, that is value half. So this value is 100 into 9.8, so this answer is also 980 Newton, and this one is also 980 Newton. Okay, now if we apply this figure, you see F1 and small f in the upward direction, and mg sin theta is the component which helping the body moving in the downward direction. So here if we apply these two component forces, you can write F1 plus f, that is equal to mg sin theta. So from here you can write F1 is equal to mg sin theta minus of f. This is our equation. Now you see, if we apply this second equation, you see here F1 in the upward direction and F and mg sin theta in the downward. So our second figure says that is F2 is equal to mg sin theta plus there is a frictional force. Now you can easily check this one, which one is the greatest force. F1 that is mg sin phi minus f, and F2 that is mg sin not phi sin theta plus f. Obviously this force is the greatest force, and this force is happens when according to this force is our figure second, and this force is according to our figure first. So you have to find out the least and greatest force. This is the greatest force and this is the least force. So you see what is the value. At first you find out the greatest force, mg sin theta, that is 980, plus f we already calculated, that is 980. So this one is 980 plus 980. So the answer will be 0.6 at Newton, 1960 Newton. And what is the minimum force? Mg sin theta minus f, and mg sin theta that is 980 and f that is 980 minus 980. So minimum force that is required to keep the mass in equilibrium, that is 0, and the maximum force is required to keep the mass in equilibrium, that is 1960. So this is all about our problem number 1. Now see problem number 2. Okay, at first write down the problem. A box of mass 4 kg is raised on an inclined plane. The inclination of the plane of the earth gradually increases. It is found that the when the slope of the plane is 1 in 3, this point you have to remember, and the box starts sliding down on the plane, and g value given, that is 9.8. At first you write down the value given. M given 4 kg, g you have to consider 9.8 meter per second square, not 10, and here which value is given? Plane, that is 1 in 3. You see this is an inclined plane, this is an inclined plane, this is the perpendicular, this is the angle of inclination. So this value is given 1 and in 3. This, when angle of inclination is 3, this height is 1, this condition is given. Okay, now you have to consider you have to calculate, find the coefficient of friction between the box and the plane. Okay, suppose there is a box of mass m, weight w, that is mg downward. So this component, same thing, cos theta, this component mg sin theta, this is balanced with normal action r, and here there is frictional force F. Now see mu, that is equal to, we know, F by r according to formula, that is according to law of friction, not mu s, not mu k, because here you have to find out only mu, that is the coefficient of friction. So F which is balanced with mg sin theta, and r which is balanced with mg cos theta. So mg cancel out, sin theta by cos theta, that is mu equal to tan theta, and tan means perpendicular by base. Here perpendicular, that is 1 given, and base is not given, but hypotenuse, this one is given 3. So when this one is 3 and this one is 1, you can easily find out this value. How? 3 square minus 1 square. So this answer will be 1 upon 9 minus 1, that is root 8, that is mu equal to 1 upon root 8. So this answer will be, check how much, this answer will be 0.35. Okay, and there is no Newton, there is no unit for coefficient of friction. Okay, this is our first part. Now you have to find out what force applied to the box parallel to the plane and will just make it move up in the inclined plane. The body is moving up, that means the friction will be detected here in the downward direction. So for second case, you draw the figure. According to second part, our figure will be looks like this way. Mg mg cos, this is the mg sine, the applied force, and friction force is directed this one. So here capital F applied, that must be just when the makes it moves up, that means external force exactly equal to the backward forces, sum of the backward forces, and sum of the backward forces, that is mg sine theta plus of F. Now you just putting this value, mg sine theta, m that is 4, g that is 9.8, sine theta that means perpendicular by hypotenuse, perpendicular 1 and hypotenuse is 3, so this one is 1 by 3 plus, and f that is equal to mu into r, and r that is balanced with here mg cos theta. So this value is 4 into 9.8 into 1 by 3 plus mu value, this one mu 1 upon root 3, mu 1 upon root 3, m that is 4, g 9.8, and what is cos theta? Cos that means base by hypotenuse. Here base, this is the base, and we already find this value, base, this one is 1, this value is 3, so base is 1 upon root 3, root 8. We calculated here, okay. So this one is base by hypotenuse, so base that is root 8 and hypotenuse that is 3. Root 8 cancel out, and by solving this one, just solve it, the answer will be 26.13 Newton. So this is the answer for our second problem. So now today I'm ending here. Solve these types of problem, go back to your exercise book, any types of exercise book you see, there are various types of problem are given related to this topic. Solve, and if there is any problem, tell me to the comment section. Today ending here, meet you in next class. Bye bye.